Today, we're plunging into a concept that, well, it's captivated humanity for ages: time travel.
It really has.
And forget what you think you know from the movies,
Okay.
because our mission here is to go beyond all those popular sci-fi notions.
Yeah, beyond the tropes.
Exactly. We're going to explore its surprising history, the mind-bending science, and the really profound philosophical questions it raises, and it's all drawn directly from the fascinating material you've shared with us.
It's truly remarkable how ancient this impulse is, the idea of imagining time travel.
Right.
The concept stretches from, the earliest myths and religious texts all the way to cutting-edge theoretical physics. So prepare yourselves, because this deep dive is definitely going to offer some truly mind-bending insights into what time is and what it might mean to move through it.
It's fascinating how truly ancient this is. So, okay, let's unpack this. How old is the idea of skipping through time? We're not talking fancy machines just yet, right?
Not at all.
Just the sheer human desire to experience another age.
That's a great question. And the sources, well, they reveal it's a deeply rooted human impulse.
Mm.
What these diverse ancient tales really show is this fundamental human longing to escape the constraints of linear time. Often through divine intervention, it highlights our deep-seated anxiety about the passage of ages, losing connection.
Okay, give us an example.
For instance, in Hindu mythology, the Vishnu Purana tells the story of King Kudmi. He visits the creator Brahma in heaven,
Right.
and when he returns to Earth, he's shocked. Many, many ages have passed.
Wow.
Then there's the poignant Japanese tale of Urashima Taro. He's a fisherman who
Right.
visits an undersea palace for just 3 days. Seems like no time at all.
3 days. Okay.
But he returns to his village. 300 years have passed. His home's in ruins, family long gone.
That's heartbreaking. And it's remarkable how these narratives from such different cultures, they share this common thread, right? This time distortion thing.
Especially.
Often through something divine or supernatural. You see similar themes even in the Abrahamic religions.
Absolutely. In Judaism, there's the Talmudic story of Hani Hamagal. He's a 1st century BC sage, falls asleep for 70 years.
70 years.
Yeah. And when he wakes up, he sees this carob tree, which he'd actually seen being planted before he fell asleep, for future generations.
Uh-huh.
Now it's bearing fruit, and it's being tended by the original planter's grandson.
Incredible.
And Christian tradition has the 7 sleepers of Ephesus, a group of early Christians, hiding in a cave around 250 AD to escape persecution.
Right. I've heard of this one.
They fall asleep, wake up maybe 200 years later, and boom, the Roman Empire is Christian.
The world completely changed while they slept.
Exactly. And this very story is also recounted in Islam, in Surah Al-Kahf of the Quran.
So this idea, waking up in a different time or returning to a vastly changed world, it's just deeply ingrained in human storytelling.
It seems so.
But then this concept kind of pivoted, didn't it? We started to see a shift from these supernatural, divine explanations towards more, well, scientific ones, even if they were still pretty fantastical, as it evolved into science fiction.
Indeed. The early vision was often sleeping through time. It reflected a simpler, maybe more passive view. Think of Washington Irving's Rip Van Winkle,
Classic.
Heck in 1819, or Edward Bellamy's Looking Backward from 1888. These characters just slept through the centuries.
Right, just passive observers of future change.
But the real breakthrough in imagination, I think, came with authors who dared to envision active manipulation. First, through magic, like Charles Dickens' A Christmas Carol in 1843, Scrooge journeys to Christmas's past and future.
Very active journey.
Very active. And we also see early interaction with the past in Pierre Boitard's Paris avant les hommes from 1861. The protagonist magically travels to the prehistoric past, interacts with creatures. That really started ushering in the modern sci-fi era.
But the human imagination, and eventually science, didn't just stop at divine intervention or magical spells, did it? When did the actual device show up? The literal time machine. That's where it gets really interesting.
Yeah, that concept emerged late 19th century. One of the earliest stories featuring time travel by means of a machine is Edward Page Mitchell's The Clock That Went Backward.
A clock?
Yeah, from 1881. A peculiar clock that when you wound it backwards, it transported people nearby back in time. Still bordered on fantasy, the mechanism wasn't really explained.
Okay.
Then, in 1887, there was Enrique Gaspari Irbo's El Anacronopete. Now, that arguably presented the first story with an engineered vessel, like a ship, specifically designed for time travel.
Ah, so a proper machine.
Getting there.
Yeah.
But it was H.G. Wells's The Time Machine, published in 1895, that truly popularized the concept of mechanical time travel and just cemented it in the public imagination.
Right, Wells is the one everyone thinks of. Okay, so we've gone from gods and magic sleep to clocks and actual machines in fiction. That's the story side. Now let's shift gears. Let's get into the intriguing world of physics. What does all this mean for the possibility of time travel in our universe?
Well, it raises some truly mind-bending questions because Einstein's theory of general relativity, surprisingly, it opens up some theoretical doors.
Really, Einstein?
Yeah. Solutions to Einstein's equations suggest that certain space-time geometries or maybe specific types of motion might allow for travel into the past or future. If these geometries or motions are physically possible, that's the big if.
Okay.
Physicists talk about closed time-like curves or CTCs. These are essentially world lines, paths through space-time that form closed loops.
Closed loops, meaning you end up where you started but in the past.
Exactly. An object could theoretically return to its own past. Kurt Gödel found a solution, Gödel spacetime, that allows for this. But it requires the universe to have characteristics that doesn't seem to have like large-scale rotation. So its physical plausibility is, well, uncertain.
Okay, but if traveling to the past were truly possible, what's the very first, most glaring logical problem that immediately pops up? The big one everyone knows.
That would absolutely be the grandfather paradox.
Right.
It's the classic thought experiment. You travel to the past and you somehow prevent your own existence. Maybe you accidentally cause the death of your grandfather before he meets your grandmother.
Which creates a huge contradiction.
A massive logical contradiction. How could you have existed to go back in the first place? To resolve this, physicists like Igor Novikov and David Deutsch proposed solutions.
How do they try to fix it?
Well, the Novikov self-consistency principle suggests that any actions taken by a time traveler were always part of history. You can't actually change history.
So you can go back, but you can't alter anything significant.
Or rather, anything you do alter was always meant to happen that way. Your actions might even be the very cause of the past events you observe, leading to a kind of circular causation, sometimes called a predestination paradox or a bootstrap paradox.
Circular causation. Okay. What's the other idea?
An alternative approach is the interacting many worlds interpretation.
Ah, parallel universes.
Sort of. The idea is a time traveler doesn't arrive in their original timeline's past, but in a different parallel universe's past. So any changes they make happen there, avoiding paradoxes in their own original timeline.
So you kill a grandfather, just not your grandfather.
Exactly. David Deutsch suggested this, though Stephen Hawking actually countered that. He argued that even if a many worlds interpretation is correct, a time traveler should still experience a single, self-consistent history within their own world. Alan Everett also raised objections, saying Deutsch's idea messes with quantum mechanics too much.
So if your actions in the past were always meant to happen, that Novikov idea, it sounds a bit predetermined, doesn't it? Like there's no free will for the time traveler.
The Novikov principle definitely leans towards a deterministic view of time.
Yeah.
Everything, including what the time traveler does, is already sort of baked in to the fabric of reality.
You're just playing a part you are always going to play.
Pretty much. It's less about changing fate and more about fulfilling it. The other interpretations, like many worlds, they offer a different kind of freedom, maybe, where you simply create a new reality rather than altering your original one.
So you're either part of an unchangeable history or you're branching off into totally new ones. Both fascinating, but very different implications.
Absolutely.
Okay, beyond these paradoxes, what specific theoretical physics concepts are explored as potential mechanisms for time travel? How might it actually work?
Right, the how. There are a few key ones that pop up in the literature. The most well-known are probably wormholes.
Like in the movies, tunnels through space.
Exactly. Hypothetical tunnels through space-time, permitted by Einstein's equations. Now, a wormhole might function as a time machine if, say, you could accelerate one end of it to relativistic speeds and then bring it back. Or if you placed one end in a very strong gravitational field. Time dilation, which we'll get to later, would cause the moved end to age less, making it relatively younger than the stationary end.
Ah, so one end is in the future relative to the other.
Effectively, yes.
Yeah.
So an observer entering the younger end would exit the older end at a time before they entered. From an external perspective, they'd travel back in time relative to the outside universe.
Wow. But are there catches?
Oh, big ones.
Yeah.
A significant limitation is you can only go back in time as far as the wormhole's initial creation. You can't visit the dinosaurs unless someone made a wormhole back then.
So it's more like a path through time than a device that moves through time.
That's a good way to put it. And the biggest hurdle is construction. Building a traversable wormhole would likely require something called exotic matter.
Exotic matter, what's that?
It's hypothetical stuff with negative energy density. Think of it as matter that repels gravity, pushing space apart instead of pulling it together. Totally alien to our everyday experience,
Yeah.
and we've never actually found any.
So, a pretty major roadblock.
A huge one. And even if you could get past that, leading physicists like Matt Visser argue that quantum effects would probably make wormholes unstable or impossible to traverse anyway. They might collapse the moment you try to send something through, like cosmic gatekeepers preventing paradoxes.
Okay, so wormholes are tricky. What else is there?
Another theoretical idea is the Tipler cylinder. Imagine a really, really dense cylinder, technically infinitely long, spinning incredibly fast.
Infinitely long. Okay, already sounds impractical.
Highly. But if it spun powerfully enough, the theory goes, a spaceship spiraling around it could travel back or forward in time, following one of those closed, time-like curves.
But the requirements.
Astronomical. The
Yeah.
density, the length, the speed.
Mm.
Building it with any kind of ordinary matter seems utterly impossible.
Right. So more theoretical curiosity than engineering blueprint.
Definitely. And Stephen Hawking himself raised a more fundamental objection to many of these schemes with his chronology protection conjecture.
Chronology protection. Sound like the universe defending itself.
That's basically the idea. He conjectured that the fundamental laws of nature actively prevent time travel, especially on macroscopic scales, particularly if building the time machine requires that problematic negative energy density. He argued it's likely impossible to build a finite time machine using only positive energy.
So the universe has safeguards.
Yep.
That covers the big theoretical physics ideas. But shifting focus slightly, what about the really weird stuff? What does quantum physics tell us about time and potential travel? Does entanglement offer a loophole?
Quantum mechanics. It's strange, but probably not in the way that helps time travel. While phenomena like quantum entanglement look like they might allow faster than light, or FTL communication.
Spooky action at a distance, right?
Exactly. But there's a rigorous result in modern quantum field theories called the no communication theorem.
Okay.
It basically proves that despite the spooky appearances, no actual information can be transmitted faster than classical signals using entanglement. Causality is preserved.
So even though entangled particles seem linked instantly across space, you can't use that to send a message faster than light or back in time.
Correct. If you could send a signal FTL, that would imply receiving it before it was sent in some reference frames, effectively moving backward in time. But quantum mechanics seems to shut that door firmly. No FTL information transfer.
Okay, so entanglement doesn't give us a free pass. But what about some of those truly bizarre quantum experiments we sometimes hear about? The ones that make you wonder if causality is, holding on by a thread.
There are definitely some mind-bending experiments. Take the delayed choice quantum eraser experiment. It seems like you can retroactively determine how a photon behaved in the past.
How does that work?
Well, basically, an experimenter can choose how to measure certain idler photons. And this choice seems to influence whether an interference pattern is observed for related signal photons that were actually measured before the choice was made.
Whoa, that sounds like changing the past.
It looks like it. But here's the catch. The interference pattern only emerges after you collect the data from both the idler and signal photons and correlate them. You can't know the past outcome until you get the future measurement results. No information is actually sent back in time to change anything. Causality is preserved, just in a very subtle and surprising way.
Okay, so appearances can be deceiving in quantum mechanics.
Very much so. There were other experiments too, like Li Jun Wang's, where light pulses seem to exit a medium before entering it, or Nips and Stahlhofen claiming FTL photon transmission via tunneling. But again, careful analysis showed that while parts of a wave might appear FTL, no actual matter, energy, or, crucially, information travels faster than light. Causality holds. It's like the front of a wave cresting early, but the message arrives on time.
It seems like every time there's a glimmer of FTL or backward time travel, physics finds a way to say, nope, causality is safe.
That seems to be the pattern, yes.
Sure.
The universe appears remarkably consistent in preventing information from traveling backwards.
Which brings us to that common argument against time travel. The absence of time travelers from the future. If it were possible, wouldn't we have met them by now? Shouldn't we be seeing tourists from the 25th century?
Right, the where are they question. It's actually quite analogous to the Fermi paradox for extraterrestrial life. If aliens exist, why haven't we seen them?
Good analogy.
The lack of future tourists doesn't definitively rule out time travel, though. There could be many reasons. Maybe time travel is never developed, maybe it's possible, but incredibly difficult or dangerous.
Or maybe they're being careful.
Exactly. Maybe it's used extremely cautiously, or perhaps travelers are disguised,
Yeah.
blending in. Carl Sagan even playfully suggests they might be here, but we just don't recognize them.
Hmm.
And Stephen Hawking offered another possibility. Maybe time travel is only possible in specific, highly warped space-time regions, or perhaps you can only travel back as far as the time machine itself was created.
Like the wormhole limitation.
Precisely. That would neatly explain why we haven't been overrun by tourists from the future. They simply can't come back to our time before the first machine exists.
Have people actually tried to, like, invite time travelers?
They have. There have been experiments explicitly designed to entice future travelers. Perth had a destination day. MIT hosted a time traveler convention. Stephen Hawking famously threw a party, a reception for time travelers, complete with champagne, but only sent out the invitations after the party occurred.
Huh. And did anyone show up?
Sadly, no confirmed travelers attended any of these events.
Yeah.
Of course, if the many worlds idea is right,
Then maybe they did show up, just in a different universe's version of the party.
that's one interpretation, yes. It keeps the possibilities open, even without tourists.
The Fermi paradox for time travelers, that's a brilliant analogy. It really makes you wonder, if we ever cracked it, could we resist popping back to see, the dinosaurs or the Library of Alexandria, even discreetly?
It's a tempting thought experiment, isn't it? The ethical implications alone are staggering.
Definitely. Okay, so for all the theoretical wormholes and paradoxes and quantum weirdness, what's the most tangible form of time travel that we actually observe and understand today? The one that's real science.
That would absolutely be time dilation.
Right. This comes from Einstein, too.
It does. It's a direct consequence of the invariance of the speed of light in his theories of relativity. There are two main types.
Okay.
In special relativity, time passes slower for objects moving at very high speeds, relativistic speeds, relative to a stationary observer.
Mm-hmm.
The faster you go, the slower your clock ticks compared to someone standing still.
And the other type?
That's from general relativity. It says time also passes slower in stronger gravitational fields. Clocks tick slower closer to a massive object like Earth than they do further away.
And we actually see this happen. It's not just theory.
Oh, absolutely. There's tons of observable evidence. One classic example is atmospheric muon decay. Muons are particles created high up, and they decay very quickly. Based on their lifespan, they shouldn't reach the ground.
But they do.
They do. Because they're traveling so fast, their internal clocks slow down relative to us. Time dilation extends their lifespan just enough for many to reach Earth's surface.
Wow.
And GPS satellites. They rely on incredibly precise timing. They have to constantly adjust their clocks to account for both effects. They're moving fast, special relativity makes their clocks run slow, and they're in weaker gravity than us on the ground. General relativity makes their clocks run fast. Without correcting for time dilation, GPS would become inaccurate within minutes.
So it's built into our everyday technology.
Exactly. This is, in a limited but very real sense, time travel into the future. A person can experience less proper time for themselves, that's the time measured by their own watch, while more time passes for everyone else.
Like the twin paradox?
Precisely. The classic thought experiment. One twin zooms off in a spaceship at near light speed, travels around, and comes back. Because of their speed and acceleration, they experience time dilation. When they return, they've aged less than the twin who stayed on Earth.
The traveling twin has literally traveled into the Earth twin's future.
In a way, yes. They've experienced less time passing for themselves.
So what does this all mean for us, practically? Can we really use this to jump, say, a century into the future with current tech? Is that feasible?
Well, time dilation is very real, but the effects are usually tiny, unless you're dealing with extreme speeds or gravity. The current limitations are immense.
Immense.
Our sources mention that to significantly slow down time, maybe by a factor of 4, you'd need something like a spherical shell with the mass of Jupiter, somehow compressed down to maybe a 5-meter diameter.
Right. So not happening anytime soon.
Not with any technology we can even conceive of right now. With our current space travel capabilities, we're talking about incredibly small differences.
Like how small?
For instance, the cosmonaut Gennadiev holds the record. He spent over 2 years, about 748 days, in Earth orbit on the Mir space station. Due to the speed, he traveled about 150th of a second into the future, relative to us on Earth.
1/50th of a second. Tangible, measurable, but yeah, not exactly a leap into the next century.
Not quite. So technically possible to travel into the future this way? Yes. Is it practical for any significant leap? Absolutely not. Not yet.
Yeah.
We're talking sci-fi levels of energy and engineering way beyond our current grasp.
Okay. So, as we kind of wrap up this incredible journey through time travel, let's explore the philosophical side a bit more. This whole concept has clearly challenged our understanding of reality and causality for ages, right back to ancient thinkers.
Oh, definitely. Philosophers have wrestled with the nature of time itself for millennia. You had figures like Parmenides in ancient Greece who held the view that time, change, it's all basically an illusion.
An illusion. Yeah.
Yeah. Centuries later, Isaac Newton championed the idea of absolute time, like a universal clock ticking away independently of everything else. But his contemporary, Gottfried Wilhelm Leibniz, he argued that time isn't an independent thing. It's just a relation between events, which interestingly kind of laid some groundwork for the later concept of space-time and relativity.
Which brings us to a really deep philosophical debate, doesn't it? Does the past and future truly exist in the same way the present does, or is only the now real?
That's the absolute core of the presentism versus eternalism debate. It's huge in the philosophy of time.
Okay, break those down for us.
So many philosophers, especially looking at relativity, argue that it implies eternalism. That's the idea that the past, present, and future all exist in a real sense. They're equally real. Time is seen as another dimension, like space. Future events are, in a way, already there on this timeline.
Like points on a map, we just haven't reached it.
Kinda, yeah. Presentism, on the other hand, is the view most people probably intuitively hold.
Mm.
Only the present moment is real. The past was real, the future will be real, but only the now actually exists.
And if only the present exists.
Then time travel, particularly to the past or future, seems impossible, right? Because there's literally no past or future place to travel to. It doesn't exist. Though some presentists try to find ways around this, arguing about truths about the past or future existing, even if the objects don't. It gets complicated.
Okay, let's revisit the grandfather paradox again, but just through that philosophical lens. Does the sheer logical contradiction of it prove time travel is impossible, philosophically speaking?
Philosophically, not necessarily prove it impossible, but it certainly highlights the constraints. Some philosophers argue that while backward time travel might be metaphysically possible, it would be logically impossible to actually change the past.
Aligning with that Novikov self-consistency idea again.
Exactly. The argument is, if you were to travel back, your actions would have to be consistent with the past that already unfolded. You couldn't kill your grandfather because, well, you exist. Your existence is proof he survived. You'd simply fail, or discover you were mistaken, or perhaps your attempt was the very thing that caused him to meet your grandmother.
You're locked into fulfilling history, not rewriting it.
That's the philosophical take aligned with self-consistency, yes.
And what about the other big paradox often discussed, the ontological paradox, sometimes called the bootstrap paradox? That idea where an object or piece of information seems to have no origin, like the watch that's always existed in a loop.
The bootstrap paradox. This is fascinating philosophically. It relates to a concept called compossibility.
Compossibility.
Yeah, it essentially means that what can happen in the past, if you were to travel there, is limited to what is logically consistent with the history that did happen. You can't create a true contradiction.
Okay.
So this again ties into Novikov's self-consistency principle. Actions by a time traveler are always part of history, leading to that circular causation. The classic example, maybe inspired by the film Somewhere in Time, is a watch. An old woman gives a young man a watch. Later, he travels back in time and gives that same watch to her younger self. She keeps it until she's old, then gives it to him.
Where did the watch originally come from?
Exactly. It exists in this closed loop with no apparent origin. Philosophically, this raises questions, especially about things like the second law of thermodynamics. Shouldn't the watch decay? Entropy should increase.
Right, it can't just loop forever perfectly.
Well, the counterargument in our sources is that entropy is a statistical law, mainly for isolated systems. A watch interacting with the world isn't isolated. It's theoretically possible, though maybe unlikely, for interactions within the loop to maintain its condition. It's not a definitive refutation. And interestingly, back in 2005, Daniel Greenberger and Carl Svosel proposed that quantum theory itself might actually provide a model for time travel where the past must be self-consistent, inherently resolving these paradoxes at a fundamental level.
Wow, so even quantum mechanics might enforce consistency. This deep dive has truly taken us on an incredible journey, from ancient myths and legends dreaming of escaping time.
All the way to the cutting edge of theoretical physics, grappling with the very fabric of space-time.
Yeah, the concept of time travel just continues to challenge our understanding of reality, of causality, pushing the boundaries of what we even thought was possible to think about.
Indeed. And while true backward time travel, visiting the past, remains a profound mystery, fraught with theoretical paradoxes and currently insurmountable physical requirements.
Right, the exotic matter, the infinite cylinders.
Exactly. But the forward time travel of time dilation, that's different. That's well-established physics. It's a phenomenon that directly shapes our modern technology, from GPS right up to space travel calculations. It's real.
So here's a final thought to leave you with. If our deepest theories of physics, like general relativity, can seriously entertain the possibility, even the theoretical possibility, of traveling to the past, despite all the paradoxes and problems, does that imply a universe far more interconnected, maybe even more predetermined than we often imagine? Or is it just a tantalizing glimpse into possibilities that are fundamentally beyond our current comprehension, something for you to mull over?